And so we are back to this diagram again. Now, continuing with what we're talking about. Now, we are talking about this diagram that you always see. That you always see. And you're asked to find out the degree of freedom. And the point is, when we have to find out the degree of variance, we know, remember the triple point, we're talking on the triple point. Okay, so we have, if at the triple point, then you have all the three mineral phases coexisting in equilibrium. So we have P is equal to 3. At the moment we come to this value of C, we have a problem. What is the composition of sillimanite, kyanite and andesite? Let's say all the minerals, sillimanite, kyanite and andesite, have the formula Al2SiO5. Let's say it has the formula Al2SiO5. So then you could write you could have AlSiO, 3 components, or you could have Al2O3SiO2, 2 components, or you could have Al2SiO5, 1 component. We take 1 component because it's the minimum number of components, right? So our C is equal to 1. And then we come to this F is equal to C minus P plus 2, and this holds up to 1 minus 3 plus 2, and this is equal to 0. Now, interesting, the degree of variance is equal to 3, or the number of variables minus the number of equations is equal to 0. That means the number of variables and the number of equations that you have is 0. Now you can ask me, so what are these equations you are talking about? What are these equations you are talking about? Where are the equations? I don't see the equations. Where are the equations? Now this is where I will explain it to you a little later. Please imagine that there are equations. And I will have to talk about it because it's not a very simple thing again. But imagine there are equations. So the number of variables here is 0 for this. The number of variables is equal to, therefore, the number of equations. And as I said, you can ask me, so where are the equations? We will talk about it a bit later. For the moment, you know from those first two chapters that, just briefly, that G is a function of pressure, temperature and composition. Isn't it? Pressure, temperature and composition. Whatever the equation is, it's a function of pressure, temperature and composition. For a pure phase, X is no more there, because for a pure phase the mole fraction is 1, so X is equal to 1. That means an equation comes in, X is equal to 1. Right. So then G is a function of temperature. So essentially when you write a reaction, say for example, kyanite is equal to sillimanite, since sillimanite has a free energy equation and kyanite has another free energy equation, and you write it kyanite is equal to sillimanite, then you will have a reaction where at equilibrium free energy of kyanite is equal to the free energy of sillimanite. So delta G, free energy change of the reaction, is equal to 0. So then you have an equation which is essentially a function of pressure and temperature. Have you understood? There is a pressure and temperature. These are the 2 functions. I will repeat again for those who may not have understood, because I have really not told you the relation between a reaction and equation. But I will come to that in great details later on. but for the moment, for a particular phase, G is a function of pressure, temperature and composition. Any phase. For a pure phase, G is a function of pressure and temperature. Your chapter 1. Chapter 1, write up 1, the first one that I said to you. And for a solid solution phase, G is a function of pressure, temperature and composition. Now every phase has a particular G value. You know, say along this line, kyanite is equal to sillimanite, they are in equilibrium. Equilibrium means G sillimanite is equal to G kyanite. That means delta G, difference of kyanite and sillimanite, is equal to 0. If so, then you have an equation for a pure phase where it's a function of pressure and temperature. So these are the variables. These are the variables. Right? These are the variables. Now, every thermodynamic equation, therefore, thermodynamic reaction is an equation where there are variables built into it. How they are used, what they are, we will see. But those are all equations. Every thermodynamic equation, reaction, is a thermodynamic equation involving variables. For a pure phase, pressure, temperature are the only variables. For a solid solution phase, pressure, temperature and mole fractions are the variables. But we are at the moment dealing with Al2SiO5, which is a pure phase. And so this applies to us. So the unknown variables in this are pressure and temperature. And this tells us that if your composition, system component is Al2SiO5, 1, C is equal to 1, P is equal to 3, and then you have the variance is equal to 0. Meaning what? Meaning the number of variables is equal to the number of equations. Right? That means if you have now two variables here, isn't it? This is temperature and this is pressure. These are the two variables in this graph. Sorry that I did not write it earlier. So, if there are two variables, then there are two equations. You can ask, sir, but there are 3 lines, so there should be 3 equations. Yes, students. Yes. There are 3 reactions. There are 3 reactions. But I tell you there are only 2 equations. I will tell you in a moment. Metamorphic petrology is a few little related things that I have to tell you. Right. We will ignore that at the moment. The only thing that you should remember at this point, before I go into great details of that every thermodynamic reaction is essentially an equation where you have pressure, temperature and compositions as the variables for solid solution phases and pressure and temperature for pure phases. Right? Correct. So now we have come to this where it is equal to 0. That means pressure and temperature, the 2 variables that are necessary for a pure phase, they are automatically generated. There is no unquantified variable. There is no unquantified variables. There are 2 variables and you have 2 equations. 2 equations. So you can solve it with the system, can solve it, and it tells you this is the pressure and this is the temperature. Right? Now, I will use a different pen. Let's say, I draw it with a different color now. Let's say the composition, I take a high pressure, eclogite facies, pellitic rock, which will have kyanite. And I can assure you that if you have analyzed that kyanite, you will get a substantial amount of chromium. Normally, you will have a lot of chromium. So now your composition is composition, that means I will write it clearly so you understand what you mean. So your sillimanite, kyanite and andalusite, if you are looking at a high pressure thing, then it contains AlFe. Remember, this is trivalent. Kyanite, AlFe, again 3 plus, whole twice SiO5. And your andalusite is Al, comma, Fe 3 plus, whole twice SiO5. So now, if I ask you for this Al2SiO5 phase diagram, what are the system components? What will be your answer? The answer will be Al2SiO5 and Fe2SiO5. Remembering that this is 3 plus. So you have two components now, Al2SiO5, Fe2SiO5. Now what happens? How many phases are there? 3. How many components are there? 1, 2. It's a 2-component system. Now if I ask you what happened here, equal to, now for this, 2 minus 3 plus 2 is equal to 1. There you go. There you go now. Now what it says, okay, if this is your system, then we have a problem at hand. What is the problem at hand? There is one unquantified variable. One unquantified variable. That means, in this case, variance is 1 for this composition of your alumini of your kyanite, sillimanite and andalusite. Your variance now is 1. That means number of variables is equal to 1 plus number of equations. That means one additional data you need. One additional data you need. That means you don't have an unique PT value. It is not a variance 1. So this triple point is no more a singular point in a pressure temperature diagram. It is a function of something else. And what is that function? What could be the variable? What are the other variables now in this new diagram? You will soon see that now you have, because of this, you have added a complication to the system. It is no more this flat thing. Now you're where the point kyanite, sillimanite and andalusite, where they coexist, now it's no more an invariant point, but an univariant line. It is now an univariant line. So this point now is no more unique. It varies. But what does it vary on? But what does it vary on? Okay, let's look at these compositions. Pressure temperatures, of course, a variable. We have it on pressure temperature diagram. So what are the variables? You have a variable. What is the variable? Listen to me at this carefully. For this composition, I can write XAL is equal to AL divided by Al by Fe3 plus. And this is in sillimanite. Have you understood? So X Fe3 in sillimanite is equal to Fe3 plus divided by Al plus Fe3 plus. That means now you have XAL and XFE in sillimanite. And you remember, this 2 should add up to 1. XAl in sillimanite plus XFe3 plus in sillimanite will add up to 1. So XAl plus XFe is equal to 1 in sillimanite. That means if you know one, you know the other. So if this is a variable, this is also, if this you know, this is automatically known. Same for kyanite, same for andalusite, you will know. These are not independently varying variable. One of them is independent variable, the other one is a dependent variable. Have you understood? So this, although you have written 2, but each of them is not a variable. One of them is independent variable. So if you know one, you know the other. So you have one variable from here, sillimanite, one variable from kyanite, and one variable from andalusite. One variable for sillimanite, one variable for kyanite, and one variable for andalusite. So in this system, how many variables do you have? Pressure, temperature, X-aluminium sillimanite, X-aluminium kyanite, X-aluminium andalusite. There you go. You have 5 variables. Remember, this is 1 minus XFe sillimanite, this is 1 minus XFe kyanite, and this is 1 minus XFe andalusite. So you have 5 variables. Have you understood? It says that you have 5 variables, not 1. Not 1, not 2, not pressure and temperature. Yes, pressure and temperature if it was Al2SiO5. If it was Al2SiO5. The moment you change this, every mineral here, all the 3 minerals, can vary its composition between the 2 end members, Al2SiO5 and Fe2SiO5, and resulting, you will have these 5 variables. Pressure, temperature is common to both in black and red, but this variable comes in. Remember, if it was pure, then XAl sillimanite would have been equal to 1. XAl kyanite would have been equal to 1. XAl andalusite is equal to 1. That means it is self-constrained. But right now, you don't know. So you have 5 variables. 5 variables that are there, built in to this particular system, out of which the variance equation tells you, give me 1. Give me 1. And I will calculate. Rest is not important. Give me 1. And I will tell you what the other 4 are. So you need 1 input and the rest can be quantified. How? We will see. How? We will see. But going into the depth of it, this is very, very crucial. Phase rule, once again, you have a bivariance, a bicomponent system. And that has modified your earlier pure phase system into one variance assemblage. Sillimanite, kyanite, and andalusite in the presence of chromium. Sorry, where did I do? What did I say? Where did I say chromium? Okay, ferric iron. It doesn't matter. If it was chromium, it would have been something else. Okay, so in this bivariant, if this is the component system components, and these are the variables, these are the number of variables, the Gibbs phase rule tells you that out of these 5 variables, give me an input of 1 variable. And I will tell you all the rest 4. How? I will tell you later. Have you understood? This is very important. So what has happened? This triple point now is no more an invariant system. It is now an univariant system. Why? You see, along at this point, pressure temperature is fixed. But if you are on this line, to fix the point, you need a variable. Say if you take this, then this will be the pressure. If you take this temperature, this will be the pressure. So the pressure and temperature values will change depending on these variables. And the Gibbs rule merely tells you, give me one. And the rest I can quantify. If you put in that I give you the value, then the variance drops to 0. If you can give the data, then the variance drops to 0 because you've given an equation. So have you understood? When you say input data, give me a pressure value. What you will say, phi P is equal to something. That's an equation. So you artificially increase the number of equations. So number of variables minus number of equations, the values. If you increase the equation, the values drops. So when you give an input value, the equation is hiked up, and so this difference becomes 0. So now you see, if you take this aluminium ferric ion system, then your triple point is not a triple point anymore. That is why I said, if your teacher asks you, what is the variance of sillimanite, coexisting sillimanite, kyanite and andesite, you have to ask him, what is the composition of your minerals? If your teacher had asked, what is the variance of coexisting sillimanite, kyanite and andesite in the Al2SiO5 system, he has told you the system. And then this blacking works. But if he has not, then I have many pens and I don't know which to use. You can ask me, what is the blue pen? We know what is your black pen. We know what is your red pen. What is this blue pen? There you go. Now what happens? This is my blue pen. Your sillimanite could contain chromium. And if you do that, then you can see C now is equal to 3. This now becomes equal to 2. And have you understood? 3 plus 3 plus 3 plus 2. So now your triple point, this point, kyanite, sillimanite, aluminium coexisting in equilibrium, it can move over space, not along a line, but on the space. So it has more variables. I will erase this and use the blue one so that you can see it. It's too crowded, this board now. So I will erase this. I will erase the black. So now I have just kept this. Yes? And I draw a line. Now, if you have this, what are the variables? Now you see, if I take sillimanite, then you would have XAl plus XFe3 plus X chromium equal to 1. Yes or no? Kyanite, X aluminium kyanite plus XFe3 plus kyanite plus XCr kyanite equal to 1. This is sillimanite. And then you have andalusite, X aluminium, andalusite plus X Fe3 plus kyanite plus XCr in sorry, this would be kyanite. This is also andalusite, and this will be andalusite equal to 1. That is it. I have written this. I hope you have understood it. This will be it. I will just write one of them. So X chromium will be what? Chromium divided by chromium plus Fe3 plus Al3 plus. This will be. Similarly, for X Fe3 plus X chromium. So now, let's look at this equation. What do you see? You see something interesting. What is it? There are 3 variables. There are 3 variables in each of these equations. Have you understood? Out of that, if you know 2, the third is automatically fixed. If you take 2, if you know 2, or if you assign values to 2 of them, the third is known. It's not a variable. It's not an independent variable. It becomes a dependent variable. And this works for all the 3 phases. So now, we look here. What we should add here? How many variables should we add here now? Excel is all there. Now we add X chromium or XFE3 plus in sillimanite, or is important, or X chromium kyanite or XFE3 plus kyanite, X chromium andalusite or XFE3 plus andalusite. So now, gentlemen of the jury, you have pressure, temperature unknown. You have these 3 unknowns. If you were red, that means it was a binary system component. And now for a ternary system component, you have to have 1, 2, 3 variable. So you will have 2 plus 3 plus any of this 3. So you will have 8 variables. You will have 8 variables. If you have 8 variables, you should have 8 equations. Then you will get the variance as 0. But Gibbs phase rule tells you that F is equal to C minus P plus 2, C is equal to 3, P is equal to 3 and 2, and this is 2. Gibbs phase rule tells you, don't be stupid, don't waste your time. Yeah? Don't waste your time to find out what value. You do one thing. Nature is telling you, you do one thing. Be more intelligent than what you are. You give me 2. And the system will find the rest. How? We will see that. How? We will see that. But this is the very, very crucial thing that you need to know. It all started, all this complication started from 1 component system to 2 component system to 3 component system, black, red, blue. You increase the variable from pressure temperature when it was black to 2 plus 5 when you had 2 components. And then you bloody added 3 more because you made the sample complicated. It all started with the system components. It all started with the system components. That's why system components are crucial. That is why system components are crucial. And that is why Gibbs phase rule should be understood as a philosophy, not as an equation. Remember, Gibbs phase rule is only helping you out. Gibbs phase rule is telling you, out of all these variables that, remember, Gibbs phase rule tell you the numbers of variables that are needed. Gibbs phase rule tells you the number of variables that are unconstrained. Gibbs rule does not tell you what are the variables that are all that can be constrained. No. Those are constrained internally by the system. How will they be constrained? They will be constrained via equations. What are these equations? These equations are reactions. We will talk about them later. But first let us digest this very crucial, central philosophy of metamorphic petrology. You can take any system and try it. Be just careful of what are you doing. And you will know, I will give you some problems to solve yourself. But this is very, very, very crucial to understand. Importance of system and phase compound.